Building Services Overview, Part 1. What are building services and where do we expect to find them? Well, these gives an example of sort of building services we tend to find in our modern commercial buildings. Cassette unit there on the top left, water heating in the middle, outdoor condenser unit for a VRF on the right. Obviously, they're connected to the ones on the left. Air handling unit, bottom left, and on the right there, boiler plant room with showing pressure vessels, which is quite common in modern plant rooms there. So why do we need these building services in our building? Well, we need to maintain the temperature in the buildings within a comfortable range. What is that range though? Ideally, in my opinion, I think it ought to be about 21 degrees. Although the government says we ought to heat our buildings to 19, I think that's not really realistic because people will start to bring in heaters from home, as shown on the picture on the left there. So I think we need to have a set point in the buildings, and that set point should be around about 21 in our commercial buildings. Obviously that will vary depending on the building in general and what goes on in that building. So why do our buildings get cold and overheat? Well, in this country, we're more bothered about heating. So we're bothered about heat loss, and our buildings constantly lose heat because they're badly insulated, such as roofs, walls, windows, drafts from windows and doors, etc., and heat being lost through the floor. So if we lose lots of heat from our building, we need our building services to work really hard to keep up with that heat loss. So what sort of services do we use in our buildings? Well, if we see on the left there, we've got a boiler. The primary function of that boiler is to provide heat. On the right, we've got a chiller, some sort of cooling system. And the byproduct of that cooling system, that chiller, is in fact heat. Well, what we need to do is try and reuse that heat that's being rejected from the cooling plant to supplement the heat that's being generated by the boilers, because otherwise that heat will go to waste. The unfortunate thing is doing that is quite difficult, especially with the chiller that's shown in the photo there. That's an air-cooled chiller, and trying to recapture the heat from an air-cooled chiller is nigh on impossible. What we could do is use a water-cooled chiller and pass that water through a heat exchanger in our heating tank there, in our hot water tank there, and transfer the heat via a heat exchanger. Obviously, we have a big demand for hot water. We need a dedicated hot water heater, as shown on the right there. But the one on the left could be using recycled heat coming from our chiller. So what sort of heat do we use? What sort of fuel do we use in our buildings? Well, years ago we used coal. Now we mainly use gas and occasionally use oil. But the government's looking to phase out fossil fuels, definitely in new builds, but in existing buildings as well. You know, the government's talking about being carbon neutral by 2050. So the only fuel that could work for us there really is electricity. And that really depends on where that electricity comes from. And we'll talk about that later. So the built environment accounts for over 50% of our energy consumption. The majority of energy consumed is for space and water heating. And that's because our buildings lose so much heat. So the space heating demand is quite high. The older the building, the poorer the energy performance. 70% of our UK housing stock is pre-1970, with probably even more of our commercial buildings being pre-1970. There's significant scope for energy efficiency improvements, with savings in space heating of up to 90% achievable. And that's really to do with insulation. So the building must be well insulated. Uncontrolled infiltration must be minimalised. Heating system most responsive. And although I've put on this local control should allow people to vary their thermal comfort to their individual needs, in reality, we need to have a set point and people need to be able to stick to that set point and dress accordingly, really. So it's important principle to consider the building as part of the HVAC system because, you know, the building requires the HVAC system to heat it or cool it, and if the building is poorly insulated and it's leaky windows and leaky doors, our building services, our HVAC system will need to work twice as hard to keep up with that heat loss. So what sort of heating systems do we use in our boilers? Well, let's look at gas boilers. So the first one, non-condensing open flue. Fairly old-fashioned gas boiler here. And these standard non-condensing boilers are generally only around about 65 to 70% efficient. Can be open or balanced flue there. This particular one is showing the open flue. And it's fairly simple this. Fuel goes in the bottom. We set fire to the fuel, in this case gas. Heat from the gas heats the heat exchanger. Cold water goes in, hot water comes out, and the hot flue gases escape out the top. Now, unfortunately, quite a lot of heat goes out the flue, and it needs to be hot flue gases to remain buoyant so that the flue gases escape. But we're losing around about 30%, 30 to 35% of our heat out the chimney, and that obviously makes this boiler quite inefficient. One of the good things about this boiler, though, it is quite simple. Now, the way that it works is it draws in air from the outside. The air goes into the combustion chamber, so draws in oxygen, burns that oxygen, expels it out through the flue. So known as conventional flue boilers, these can be back boilers or wall mounted or freestanding. By allowing the flue gases to retain their high temperature, the natural force of hot air rising creates a chimney draft, takes out the flue gases, but also takes out a good proportion of the heat. Need to be careful though that there is sufficient air for the combustion process to take place, because if there's insufficient air, there's potentially for poisonous gases will be carried into the room or into the area where people are situated. Now, moving on a few years, we've now got a balanced flue boiler, and now this boiler, the flue of this boiler contains two sections, an outer and an inner section, and it draws in the air through the outer section of the flue, thereby not using any of the air in the conditioned area. Transports the exhaust gases out through the centre of the flue, still quite inefficient, around about 72 to 75% efficient, slightly more efficient than the previous boiler because the flue is shorter. Care should be taken though where the flue gases escape to, because the flue is at a lower level, it could be escaping into perhaps an open window or in through an air brick. So these balanced flue consists of two ducts, one inside the other. Fresh air for the combustion is taken through the outer duct, and products of the combustion are taken to the central duct. Obviously, it takes some heat out there as well. Care should be taken where to position the flue. Now, with these boilers tend to be quite a lot smaller and can be fitted into habitable rooms such as bedrooms and bathrooms in domestic premises, and also they can be put in cupboards if necessary. Now, most boilers now are fan assisted. The diagram here shows a non-condensing fan assisted boiler. So this one, rather than reliant on the buoyancy of the flue gases, we use a fan to draw the air in, goes through the combustion process and blows the flue gases out through the centre of the flue. It tends to be more efficient, around about 80% efficient, as opposed to the earlier one at 65 and the balanced flue at about 75. Problem with this boiler is there's more to go wrong. We've now got various sensors in them, we've got electric fan, we've got electronic controls, but most boilers now are fan assisted, either condensing or non-condensing. And we can see on the right there's a grill over the flue. Still need to put a grill over the flue if people can touch it, because there's still quite a lot of heat escaping out through the flue. So most boilers now are fan assisted, small cross section areas. Flue provides the fresh air and the burner removes the combustion through the centre of the flue there. As with balanced flue boilers, can be fitted into cupboards and habitable rooms. And again, care should be taken where the flue discharges. Now, different sorts of boilers we could have in our these two here show dwellings, but obviously it's the same in commercial buildings. We could have a combi boiler or a standard boiler. Some of you may have combi boilers, they're quite popular in new builds, and some of you may have the old-fashioned standard system. Now the combi boiler, it tends to be favoured by builders and developers and smaller households because it tends to only do one thing at the same time. Also, when you look at the pipe work and what's involved in the installation of it, there's a lot less involved there. There's no tanks and pumps and header tanks in the loft, etc. The disadvantage of that is it doesn't have any sort of backups. If the boiler stops, everything stops, and if the water supply stops, again everything stops. Now with the standard system, if the water supply fails, we have a tank full of water in the loft there as a bit of a buffer to top our system up. If the gas supply fails, we generally have an immersion heater in the hot water tank situated on the first floor. So we've still got some way of heating up our hot water, albeit our heating system wouldn't work if the boiler wasn't working. So this essentially is an instantaneous hot water heater. The water goes into the boiler, it's instantly heated up in the boiler, the fan comes on, that gets rid of the flue gases, water arrives at the tap there and comes out hot after a few seconds of the boiler starting there. A good thing about that is it only heats up the amount of water we need to use at that time. The bad thing is it can't cope with 2 or 3 things at the same time. So if 2 people are using the water, the system can't cope with that. So Combi is a combination appliance, provides heating and on-demand hot water. One of the good things about this is there's no need for a hot water cylinder and there's no need for a tank in the loft there because it gets its pressure from the water mains. Tends to be a lot more pipes than a normal boiler, than a standard boiler there, so quite easily recognisable by the amount of pipe work. The good thing about the combi boiler is the system contains all of the components within the boiler itself, which makes the boiler system more compact and neater looking. No need for a cold water feeder expansion tank, so that's good because storing water in loft is what we used to do years ago, but we've sort of moved away from that now, perhaps with the Legionella disease in mind. And also in our loft areas, we tend to occupy that area because space is at a premium nowadays, either at home or for offices. The bad thing with a combi though is there's lots of moving parts and there's potential for things to go wrong. Any one thing could stop the combi from working and then we wouldn't have hot water or heating. Also, that gas combi system is better suited to smaller households or smaller water or a fewer number of outlets there because it will only tend to do one thing at a time there. If we ask it to do 2 or 3 things at a time, like hot water downstairs and shower at the same time, it won't cope with those 2 things. So the condensing boiler. So this can either be a condensing normal, a condensing standard, or a condensing combi. So the normal system, again the standard system, can either be condensing or your combi boiler can be condensing. Has the highest efficiency of all the boilers at round about 92%. Uses a double heat exchanger to take as much heat out of the flue gases as possible. The condensate is slightly acidic. So we can see the plastic pipe leaving the bottom of the boiler there, and that will always be the condensate pipe. If we put the condensate into a copper pipe or an aluminium pipe or a steel pipe, it would quite quickly corrode away at the pipe. So how does this work then? Well, again, looking at on the left there, the diagram on the left, which we looked at with the normal fan assisted boiler, non-condensing. Cold return from the radiators in the morning. First thing in the morning, we start the system up. The cold return from the radiators goes straight into the heat exchanger element of the boiler and is heated up via the burner. Heat flue gases escape out the top. Now on the condensing system, rather than the cold water going straight into the heat exchanger area, it actually passes across the flue first. And of course, if the boiler is running, the flue is hot. And what it does, it picks up heat from the flue, therefore preheating the water before it goes into the heat exchanger section of the boiler. So thereby taking less gas to heat it up to the required temperature. And obviously, if we run that cold water pipe through the hot flue, condensation forms on it and comes out the condensate drain there. So if you've got a condensing combi or condensing standard boiler at home, you'll notice that when it's running, condensate drips out the pipe, and also from the flue, we tend to get steam coming out there because the flue gases are heavily laden with condensation. So condensing boilers are water heaters fueled by gas and oil, achieve higher efficiency, typically greater than 90% on the higher heating value. In many countries, United Kingdom included, the use of condensing boilers is compulsory or encouraged with financial incentives. But it's worth remembering that in 2025, the government is looking to ban condensing boilers in new builds. So like I said in one of the earlier slides, the only alternative for that is at the moment heat pumps, and heat pumps are electric. Other alternatives might be hydrogen boilers, but I think we're a long way off at the moment with hydrogen by having hydrogen in the gas mains rather than natural gas. Tests are going ahead with hydrogen, but whether or not that'll come about, we'll have to see on that. So the flues on our condensate boilers, on the domestic style ones on the right, are generally made of a plastic material because if they're aluminium, they quite quickly corrode away. You'll note with this flue, it's not sealed to the wall of the building, which is quite bad practice. It needs to be sealed there so that flue gases are not drawn back into the building. On the left, we have a condensing boiler flue there, a stainless steel one coming from a commercial boiler or an oil boiler. So one of the hot flue gases produced in the combustion process is water vapor, and generally that's a slightly acidic, and that's 3 to 5 pH there, so it can corrode away at aluminium. Typically increasing efficiency can be as much as 10 or 12% when it's working in the condensing mode. So our commercial boilers work exactly the same as our domestic ones we've just looked at, but are just larger and work obviously on a larger scale. As we see on the left there, we've got multiple boilers. Generally in commercial premises we have multiple boilers because what we find is that boilers work better when they're working harder. So if we have one large boiler that's just ticking over, it's not particularly efficient. So what we tend to do is have one boiler working hard, and as more and more heat is needed, more and more boilers come onto line. Also gives us the additional benefit of when one of them breaks down, we can maintain that one and use the other boilers in the system there. Now, one of the latest boilers out there is this Hovel high efficiency boiler. Efficiency up to 95% can be achieved. But even that is still not really efficient enough if we're looking to move towards being carbon neutral by 2050. And even putting that into a new build now, we struggle to actually make the building comply to building regulations because of only the 95% efficiency. So if that boiler there is not good enough, what sort of efficiency are we looking at? Now the other option, and probably the only option in the future, is heat pumps. Obviously existing buildings will continue to use boilers, but new buildings will start to use heat pumps. Now heat pumps, first one we're going to look at air source heat pump. Now the air source heat pump absorbs heat from the outside air, and in doing so it's quite efficient. It uses 1 kilowatt of energy to absorb 3 or even 4 kilowatts of heat, and by doing so that makes it 300 to 400% efficient. Heat pumps have some impact on the environment as they need electricity to run, but the heat they extract from the air around and the ground, etc., is being constantly replaced there. So this compared to the boiler is 90% efficient. The heat pump, the air source heat pump, is 300 to 400% efficient. So you can imagine from a building regs point of view, or from a carbon emissions point of view, a lot more efficient, and that gives us, that is the future of our heating systems. So the output from the air source heat pump is not fixed and will vary in certain conditions. Basically, they will work for an outside temperature as low as 2 degrees centigrade, and I think we can manage with that in this country. But one of the downsides is they only produce water of round about 35, probably running up to 40 degrees. And radiators tend to have water in them round about 65 degrees. So they don't work that well with radiators. Where they will work well, though, is with underfloor heating. So our new builds in the future may tend to be heated with air source or ground source heat pumps using underfloor heating. Also, you've got to have somewhere to put it. So you'll need a space outside of your building. Obviously your boiler is inside your building, but you need a space outside for the unit to be fitted on the wall or ground. If we fit them on the ground, we need to be aware of the fact that they can drag in debris and leaves and stuff like that. So we need to make sure they're in a clean area. Is your building well insulated? Well, since air source heat pumps work best with at a lower temperature, as it were, we need to make sure we don't lose that low grade heat. So our building needs to be extremely well insulated, which works well on new builds, but they can struggle on existing builds because we sometimes struggle to get the insulation level up high enough for them. What fuel will you be replacing? Well, as bad as I've suggested gas is better of the other options. If we think about instantaneous electric, coal or oil, gas is a lot better than those. But if we're replacing those fuels, we'll have a better return on investment there. What type of heating system will you use? Well, as I've already said, it really ought to be underfloor heating. We could in fact double or treble the size of our radiators and run them at 40 degrees, but nobody really wants radiators everywhere on their walls, etc. So I think underfloor heating will become more and more popular, and I think in the commercial environment underfloor heating works well because it gives us more wall space, and we're not worried about things being stuffed down the back of radiators at public areas and stuff like that, etc. So two sorts of heat pumps. On the right we've got air source heat pump, and on the left we've got a ground source heat pump. Both of them absorb heat and transfer it into a water circuit. The air source heat pump absorbs heat from the air outside, and the ground source heat pump absorbs heat from the ground. And ground source heat pumps are even more efficient, of an efficiency of 5 to 1 as opposed to 4 to 1. So that's 500% efficient. That's because the heat of the ground tends to be more constant than the heat of the air outside. So if you have the opportunity for underfloor heating, it'd be more efficient than radiators because the water doesn't need to be so hot. You'll still have fuel costs, but they'll be electricity only. You won't have a gas bill, it'll just be electricity. If your old heating system was inefficient, you're likely to see lower running costs, but you've got to take into consideration that electric's expensive as opposed to gas. So electric at the moment is about 4 times more expensive than gas. What we need to do is thinking of better places to get the electricity from, which we'll look at that later on in the course. What about water heating though? If we use the heat pump to heat up our water, potentially that's only about 40 degrees. So what we need to do is boost it from that 40 up to 60/65. And the way that we can do that relatively easy is by using PV panels powering an immersion heater. Also, you need to learn how to use the controls. Air source heat pumps and ground source heat pumps work best when they run 24/7. They're on all the time, as it were. So if we use them like a normal boiler system, turning them on and off, they don't work that well. So the air source heat pump absorbs heat from the air outside, transfers it into the hot water cylinder, preheats the water. Quite a lot of the time, they heat radiators upstairs and underfloor heating downstairs. With the ground source heat pump, absorbs heat from the ground, which tends to be more constant than the air outside. Again, transfers heat into the hot water cylinder and into radiators or underfloor heating. Now, one of the drawbacks with ground sources, we need to in fact have quite a lot of ground. We can see on the left of the slinky loop method, if we have a smaller amount of ground, we can dig trenches. If we have a large amount of ground, though, we can dig out what we call a larger area and put in the horizontal loop there, as demonstrated on the right. But that tends to be more of a construction site project rather than a retro. If we haven't got ground at all, much ground, we can actually put in the vertical loops. And as extreme as that might seem, that is becoming quite popular. Get the boreholes go down about 100 to 150 meters, absorb heat from the ground. And that can work quite well in city centres, because the ground in city centres tends to be quite warm for things like sewers and underground tunnels and things like that. But obviously it's a challenge of where we drill the holes. We can extract heat from water, as we look at the pond loop there. That pond is nowhere near big enough in proportion to the size of the house, though. Where it does work better is in running water, so the heat is constantly replaced there. The horizontal loop there on the right there tends to be the most popular at the moment. So the efficiency of heat pumps, although I've talked about 300, 400, 500% efficient, it's measured in something called coefficient of performance, COP. So a COP of 3 is in fact 300% there. Now the government gives us something called RHI, Renewable Heat Incentive, for installing these heat pumps, because obviously they've acknowledged the fact that they are quite expensive, or more expensive than boiler. An air source heat pump is about £6,000 or £7,000, as opposed to your boiler, which is probably £2,000 to £3,000. But looking at the figures there on the screen, we can see those figures there are guaranteed for 7 years, and those figures are for a 4-bedroom detached house there. And basically we're getting about £1,700 a year. So in 5 years, we'd have seen a return on investment there. And obviously the column on the right hand side there shows the carbon savings. So if we purely after carbon savings for carbon emissions, etc., we can see the savings there, quite substantial against coal and LPG. Now, ground source heat pumps cost considerably more, as you can imagine, to install, because we've got to dig up the ground. So the government gives us a more generous RHI, a more generous incentive. And we can see the figures there add up to about £4,500 a year, as opposed to a gas system based on a 4-bedroom house there. And that again would see a return on investment in about 5 years, and the payments are guaranteed for 7 years. Now, if we're going to use a heat pump, one of the better systems is the underfloor heating. So wet underfloor heating systems, not to be confused with electric underfloor heating, where we have electrical elements going under the floor. They're quite expensive to run. But wet underfloor tends to take the heat either from the boiler, running a condensing boiler to lower temperature can work well, or heat pumps are ideal for this situation, because the water tends to be round about 40 degrees, and that's ideal temperature for a heat pump there. We can see how the pipework is set out in our commercial buildings there. We've gained a similar sort of situation with domestics as well. But one of the good things with underfloor, it gives us good controllability of individual zones. So we can see on the picture there, these may be individual rooms or offices or classrooms or workshops or things like that. Each room can be controlled individually via a manifold. So on the bottom left there, the distribution manifold works by sending out hot water to different areas, which is controlled by things what's called solenoids, which are like electronic switches, and they're shown at the bottom with the wires coming from them. So they get the signals from the room thermostats, which are situated in individual rooms, and open and close the circuits as necessary for those areas. Picture on the right there showing a house there. Each room can be separately controlled, so it's good controllability of individual areas there. Now, what about electric heating in our building? Well, generally that's quite expensive, and it's always had bad press, electric heating. Electric heating is always 100% efficient. Whatever we put in is what we get out. We put 1 kilowatt in, we get 1 kilowatt out. Now, electric was always considered bad because it wasn't a problem with the electric heating, it's a problem with the buildings it was put in. If you put electric heating into a badly insulated building, it will cost you a lot of money to run. Also, from a carbon emissions perspective, it's not particularly good because the carbon emissions of electric, based on current calculations, is about 4 times as bad as gas. Now, electric heating on well-insulated buildings is not too much of an issue, mainly because if we're not using much electric, albeit it's slightly expensive, but if our building is well insulated, we're not using much, so we're not paying that much extra there. So the good thing about electric heaters, relatively simple, clean firing, no emissions, no problems about running gas supplies, no problems with flues coming out into areas. The disadvantage though, higher energy charges can result in higher operating costs there. Now, oil boilers don't tend to get so many of those nowadays. We're always the #1 choice where we didn't have gas. When the oil arrives on site, it's quite efficient. It's just as efficient, or if not more efficient, than gas. But when we look at the carbon emissions of oil, we take into consideration the delivery process, and unfortunately, it comes out quite badly in carbon emissions and bad in the building regulations aspects there. Also, oil is quite unpredictable and can be quite expensive in certain times of the year. LPG is in fact similar to use like normal gas, but is in fact the worst fuel out there for carbon emissions, and also it's quite expensive to run. Now, district heating has become quite popular over the last few years, heating networks as some people call them. So district heating is a system for distributing heat generated from a centralized location for residential and commercial heating. Heat is often obtained from cogeneration, CHP. So these are plants which actually generate electricity, and we use the rejected heat from them. According to some research, district heating with combined heat and power is the cheapest method of cutting carbon emissions and is one of the lowest carbon footprints. But we are tending to move away from CHP because CHP tends to be powered by gas. Most CHPs do, and because obviously gas is a fossil fuel, we are getting emissions out there, and we need to move away from gas in the future. So some sort of fuel there provides heat into a boiler or incinerator there, a supply network which can be challenging in city centres, and heat exchanger providing heat into various areas. So have a single heat source works best where there's a cluster of houses or buildings in close proximity. District heating works by heating water and is then pumped round an underground district heating ring main. What sort of fuel though for that district heating? Could it be electricity? It's unlikely. Electric's expensive and is bad for carbon emissions. Oil. Years ago we used oil quite a lot, but now again it's the delivery process of the oil and high carbon emissions. Biomass could be an option, but biomass, although it ticks quite a few boxes for building regulations and carbon emissions, it's quite a difficult fuel to use. We need quite costly and intrusive storage of the biomass fuel, and also maintenance is quite difficult and is quite messy. A lot of people just don't get on with biomass systems. Natural gas at the moment, most of the systems are natural gas, but as we move away from natural gas, we're almost certainly not going to go to coal, which is the one shown under it there. Future energy source, what could that be? Well, things that, when we looked at that second slide today and we looked at rejecting heat from our cooling plant, what about cooling plants and data centers and department stores and things like that, all dumping their rejected heat into the district heating main? Also burning of refuse, burning of waste there, that could put heat into the district heating network, and that then could power commercial, industrial and residential buildings there. Now the biomass boilers we've just mentioned quite briefly. Quite a few people use biomass boilers, although I have said they are quite a challenge to use. This particular one shows, for me, it's not pure biomass, it's actually manufactured pellets, and we've got to be careful. There is a process in manufacturing those pellets, and where do they come from? What about transporting the pellets? And that's all got to be taken into consideration. It can be an affordable heating fuel. Although the price of wood fuel varies considerably, it's often cheaper than other heating options. It also qualifies for the RHI, the Renewable Heat Incentive, so it can be quite generous for putting it in on RHI. It's also a low carbon option, because when we burn fuel, it gives off carbon dioxide, and when wood grows, it absorbs carbon dioxide, so it's actually quite neutral. But as I said earlier, a lot of people don't get on with biomass boilers. Biomass is defined as biological material that's come from plant matter, produces heat by burning this organic material. I think what can work well with biomass though is in rural areas where we've got rotational crops, municipal tree cuttings, industrial wood waste going into a local chipping and storage depot, powering a district CHP, and then that in turn powers schools, commercial units and houses, etc. Also, what can work quite well is this sort of boiler here, which burns straw bales. This particular one, we get the straw bales, it's placed inside the boiler, set on fire, oddly enough with the blow lamp that's shown on the picture there on the gas bottle. Probably not a good place to store your gas bottle next to the boiler, but that's another topic. Then the fuel there is coming from burning the straw, which powers the district heating network there. That particular boiler provides heat to these flats here and craft workshops. It's on a country estate where they used to have oil powering the system. And on the right there, it shows a plate heat exchanger where we transfer heat from the heating network to each individual unit. And on the right of the pipework there, we can see heat meter. So each unit is charged for the amount of heat that they take out of the system. Now that combined heat and power we talked about earlier. So CHP, combined heat, is a process which both heat and electricity are produced simultaneously on site, has the effect of reducing the metered energy supply to the building. CHP systems are common where heating and electric power are needed simultaneously. Don't work that well in offices because we don't need that much heat in offices. We don't use them for the heating systems because we need to think about the summer. What would we do with all the heat in the summer? But on places like hospitals, kitchens, halls of residence, laundries, we still need the hot water in the summer, so they can work well there. Also, they can work well at leisure centres. The reason they work well, CHPs, is because when the electricity is generated at central power stations, around 60 to 65 of the primary energy is rejected as waste heat to the atmosphere. So what we want to be able to do is use that heat. And what our CHP is our own local power station. CHPs produce twice as much heat as they do electricity though. So we need to be able to use that heat. So if we can't use the heat, a CHP won't work for us. Looking at this picture on this slide here, we can see that the conventional system on the left has an overall efficiency of round about 48%, using a boiler for heating and power station electricity. On the CHP though, on the right, if we use the heat from the CHP and we use the electricity from the CHP, we actually get a combined heat and power efficiency of 85%. So again, quite favourable for new builds and building regulations because they tick a box to get it past building compliance. So basically what they are is a large gas engine that runs like an internal combustion engine. Cold water comes in to the engine, is heated via the engine through the circuit of the engine, usually goes through the exhaust system as well, and is then pumped back into the building hot. On the end of the engine is a generator, and the generator generates electricity when we use that electricity in the building. Now CHPs require maintenance, so that needs to be factored into the equation when we have a CHP. Some people probably don't maintain their CHPs as well as they ought to, and they are quite expensive to maintain. So although we're saving money on energy and we're saving carbon emissions on losses, etc., we need to factor in the maintenance for the CHP. Now we can get micro CHPs, but I think this is probably at the moment a little too complex for most environments. These micro CHPs again generate heat and electricity, but I've not really seen a lot of these about. I think the bigger CHPs work quite well, but the micro CHPs might tend to be a step too far for us at the moment. Biomass CHPs can work quite well in areas where we've got quite a low demand, a low electric supply, electric capacity. So if we're in an area where the electric supply is not big enough, we can use biomass CHPs. And then in rural areas, we might have a good supply of the actual biomass. They tend to work like, well, for want of a better word, gas turbine engines. We can see that the combustion chamber there in the gas turbine engine powers the generator at the end. Cold water goes in, hot water comes out, small bit of waste heat comes out the top, and it drives the generator. Benefit of the CHP: a reduction in the cost of energy can improve competitiveness of industry, and that could obviously help our industry there. Also enhance security of supply, making energy go further. Also flexible responsive heating supplies there, and also energy, if our energy goes off there, we've got our own generator. Also to reduce the overall demand on centralized power stations, such as large scale coal or gas fired power stations. A lot of our power stations now are getting quite old, and this can take the place of our power stations. It is in fact our own little power station, isn't it? We use the heat and we use the electricity from it. Here's an example of one in a development in central London. It's a combined heat and power in a in an energy centre using a CHP and 4 gas condensing boilers. Now the gas condensing boilers are obviously quite efficient, but not really efficient enough to actually satisfy building regs compliance. So what the builder has done, the developer has done, is put in a combined heat and power, because that ticks a box for building regs compliance. So the actual CHP there supplements the heating of the hot water and also provides electricity to the building there. But it's essential again that if that is used regularly, it needs to be maintained regularly. That provides the heat to what we call heat exchanger units. So each flat in each commercial unit, rather than having a gas boiler, has one of these HIUs, heat exchanger units. So the hot water from the heat network, from the CHP, flows through this unit, and we can see the 2 heat exchangers inside, one for domestic hot water and one for heating. And this also has a heat meter in, which measures the amount of heat that's used from the network there. Similar sort of components to our combi boiler, etc. Pressure vessels and pressure gauge there. It works on a pressurized system. So what we can do again with our CHP is also provide cooling. If our CHP is running in the summer and we don't want all the heat coming from it, we can pass that heat through what we think called an absorption chiller. and the absorption chiller there can provide chilled water to our cooling system. This only tends to work where we've got waste heat. We wouldn't actually put heat into an absorption chiller from a gas boiler because that would be quite an inefficient way of doing things. But if we've got rejected heat from a CHP or from another process, that could work quite well. Quite complex, though, absorption chillers, and quite expensive. Often find them at places like hospitals where they might use larger networks for heating there. Well, that covers us for part one. Thanks for listening. If you've got any questions, we'll obviously discuss those when we do the live hour in a month or so. And I'll speak to you all again on part two. Thank you.